The spring air hung heavy inside that naval warehouse in Annapolis, Maryland. May 1945. The war in Europe had just ended, but Dr. Robert Goddard stood frozen in place, his eyes locked on something that shouldn't exist. Not here, not yet. His hand trembled as he reached toward the sleek metal cylinder towering before him. 46 feet of German engineering that seemed to mock every rocket he'd ever built in the New Mexico desert. Throat cancer had already stolen most of his voice, reducing it to barely a whisper. But in this moment, surrounded by Army officers and Navy engineers in the dim warehouse light, Goddard didn't need words. The rocket spoke for itself. For 2 decades, he'd been screaming into the void, begging Washington to listen, to fund, to understand that liquid-fueled rockets were the future. They'd called him a dreamer, a lunatic. Now standing in that warehouse with his fingers against the cold aluminum skin of a German V-2, Goddard understood something that would haunt American rocket science for the next decade. The Germans hadn't just built a better rocket. They'd built an entire world America didn't know existed. What Goddard couldn't have known, circling that massive missile with death already whispering in his chest, was that this single examination would expose a technological canyon so deep, so impossibly wide, that American scientists would spend 15 years clawing their way back to even ground. This wasn't a competition anymore. The V-2 wasn't just advanced, it was alien. Technologies that didn't exist on American soil. Engineering solutions to problems U.S. scientists hadn't even thought to ask. Manufacturing precision so perfect that American factories, even at their wartime peak, couldn't dream of replicating it. The rocket sitting in that warehouse was living proof that while America had one brilliant man working in isolation, Germany had Peenemünde, a sprawling research empire staffed by thousands of scientists, fed with unlimited funding, and given a 7-year head start on weaponized rocket technology that would reshape everything: warfare, power, and the race to touch space itself. The story of how America discovered it was living in the past actually begins weeks earlier, in April, when American boots hit German soil and stumbled onto something that would rewrite the future. April 11, 1945. The Harz Mountains, central Germany. Soldiers from the U.S. 3rd Armored Division descended into the tunnels near Nordhausen, expecting another weapons cache, maybe some desperate last stand. What they found instead made grown men stop breathing. An underground factory complex called Mittelwerk stretched into the mountain like a cathedral built for war. Miles of tunnels carved straight through solid rock, production lines running deep underground where bombs couldn't reach them. V-2 rockets in various states of assembly, some complete, some just skeletons. Components stacked in warehouses that seemed to go on forever. Technical documents piled in rooms like snowdrifts of knowledge. And everywhere the evidence of horror. Emaciated prisoners from the Mittelbau-Dora concentration camp. Some barely alive, who'd been worked to death building Hitler's revenge. Major James Hamel, Army Ordnance, walked those tunnels with his jaw hanging open. The Germans had been manufacturing 600 V-2 missiles every month. Each rocket required 50,000 individual parts. The precision machining, the quality control systems, the sheer logistics of moving all those components through underground assembly lines while the Reich collapsed above them. It was an industrial achievement that seemed impossible for a nation supposedly bleeding out in its final days. But Hamel understood something the infantry grunts didn't. These weren't just weapons sitting in the dark. They were keys to the future, and the Soviet occupation zone was scheduled to take over this entire region in a matter of weeks. Every document, every component, every single rocket would fall into Stalin's hands unless America moved faster than it ever had. Within hours, Colonel Holger Toftoy received orders from Washington that were simple and urgent. Get the rockets. Get the documents. Get everything out before the Soviets arrive. What followed became known as Special Mission V-2, one of the most critical intelligence operations in the war's dying days. American troops worked through the night, loading railway cars in a frenzy. 341 rail cars stuffed with V-2 components. Enough hardware to assemble roughly 100 complete rockets. Technical documents by the ton, all of it racing against the clock toward the port of Antwerp, where Liberty ships waited to carry America's captured treasure across the Atlantic before anyone could stop them. By late May, the first crates arrived at White Sands Proving Ground in New Mexico's Tularosa Basin, and Army engineers started unpacking what they'd stolen from the future. With each crate they pried open, with each technical schematic they unrolled, the true scale of German achievement became clearer and more terrifying. The V-2 rocket, designated Aggregate 4 by the men who built it, stood 46 feet tall and tipped the scales at nearly 28,000 pounds at launch. It could deliver a 1-ton warhead 200 miles downrange with accuracy that was, for the era, shockingly good. But those numbers, as impressive as they sounded, barely scratched the surface. The real shock came when American engineers started pulling the rocket apart to see what made it scream. The engine sat at the base, a massive combustion chamber capable of producing 60,000 pounds of thrust, and when American engineers who'd studied Goddard's work saw that number, they felt something close to despair. Goddard's largest rocket engine, after years of trial and failure and funding fights, had achieved 985 pounds of thrust. The Germans had created an engine 60 times more powerful, and they were mass-producing them like automobiles. Dr. Theodor von Karman, director of the Jet Propulsion Laboratory at Caltech, was among the first American scientists to truly examine a V-2 in detail. His team had been developing rocket technology for the Army since 1942, working on what would eventually become the Corporal missile. When von Karman laid eyes on the V-2's propulsion system, his assessment was brutally honest. "We are at least 7 years behind, maybe more." The propulsion system alone represented breakthroughs stacked on top of breakthroughs. The combustion chamber used a double-wall design that was pure genius. Alcohol fuel flowed through the outer jacket before entering the chamber, simultaneously cooling the walls and preheating the fuel before ignition. This regenerative cooling system solved one of rocketry's most fundamental nightmares, preventing the chamber from melting under combustion temperatures that hit 5,100 degrees Fahrenheit. But nothing shocked American engineers quite like the turbopump. At the heart of every V-2 sat a steam-driven turbine spinning at 4,000 revolutions per minute, powering centrifugal pumps that forced fuel and liquid oxygen into the combustion chamber at 125 liters per second. The turbine itself generated 600 horsepower, driving pumps that had to handle cryogenic liquid oxygen at minus 297 degrees Fahrenheit, while operating at pressures that would rip conventional pumps to shreds. American engineers stared at this device like archaeologists discovering technology from another civilization. The turbopump represented 7 years of German development, incorporating metallurgy, precision machining, and engineering solutions that simply didn't exist in American industry. The turbine blades were forged from nickel-chromium alloys that could withstand both hellish temperatures and rotational forces that would tear lesser materials apart like wet paper. The pumps featured seals that prevented cryogenic liquid oxygen from leaking while spinning at speeds where the slightest imbalance meant catastrophic failure and a fireball that could vaporize everything nearby. Lieutenant Commander Robert Truax, a Navy engineer who spent weeks examining the V-2's propulsion system, wrote in his classified report words that still sting today. "The German turbopump isn't simply ahead of American technology. It is technology we do not possess. Building even one duplicate would require developing entirely new alloys, new casting techniques, new manufacturing processes from the ground up. We estimate 18 months minimum to create a single working prototype. And that's assuming unlimited funding and access to materials currently unavailable due to post-war shortages that have crippled our supply chains." Then engineers opened up the guidance system, and the technological gap yawned even wider. The V-2 used an analog computer called the Mischgerät, developed by Helmut Hölzer, that integrated inputs from gyroscopes and accelerometers to control the rocket's flight path in real time. 2 free gyroscopes, one controlling pitch and the other handling yaw and roll, constantly measured the rocket's orientation as it screamed toward space. A pendulous integrating gyroscopic accelerometer, the first of its kind ever deployed, measured acceleration and integrated it over time to calculate velocity with shocking precision. When the rocket hit its programmed velocity, typically around 3,500 miles per hour, the guidance system cut the engine and let physics do the rest. The sophistication of this system left American engineers speechless. The gyroscopes were manufactured by Chrysler with precision tolerances that American firms simply couldn't match with existing machinery. The analog computer processed multiple inputs simultaneously in real time, sending control signals to 8 different control surfaces, 4 external rudders mounted on the tail fins, and 4 graphite vanes positioned directly in the rocket's exhaust stream. These vanes, sitting in temperatures exceeding 5,000 degrees, were made from specially manufactured graphite that could withstand the inferno, while providing steering control during the critical first 60 seconds of flight when aerodynamic control surfaces were useless. Dr. Charles Stark Draper from MIT, America's leading expert in guidance systems, examined the V-2's controls with something approaching professional awe. Draper had spent years developing gyroscopic instruments for aircraft and submarines, pushing the boundaries of what was possible. When he saw what the Germans had built, he immediately recognized innovations his own laboratory hadn't even conceived. They solved the integration problem, Draper noted in his technical assessment, that would circulate through classified channels for years. They created an accelerometer that doesn't just measure force, but actually calculates velocity by integrating acceleration over time. This is the first fully autonomous electronic active control system ever deployed on any vehicle in history. It's essentially fly-by-wire decades before anything in aviation, and it works flawlessly under combat conditions. But perhaps nothing revealed the brutal truth of American technological inadequacy more than the manufacturing quality itself. American engineers examining V-2 components found precision machining that exceeded peacetime commercial standards, let alone wartime production. Welds were absolutely perfect, not a single flaw visible even under magnification. Tolerances were measured in thousandths of an inch throughout the entire assembly. Components experiencing high stress loads were overbuilt with safety margins that American designers, constantly constrained by material shortages and cost considerations, would never dare specify. An Army ordnance officer examining the turbopump assembly wrote in his report something that captured the essence of German engineering philosophy. Every component appears designed to survive worst-case scenarios that would never occur in actual operation. The Germans built for absolute reliability under combat conditions. The fuel lines include redundancy we would consider wasteful in peacetime. The electrical system has more circuit breakers than any reasonable design requires. The structure is heavier than optimal weight calculations demand. This is engineering from a nation with unlimited resources to build things right the first time. Not engineering from a nation scrambling to build things cheap and fast. The electrical system alone represented sophistication beyond anything in American rocket practice. The V-2 used a 24-volt architecture with generators driven by both the main turbopump and a separate auxiliary turbine for backup power. American rockets, when they bothered with electrical systems at all, employed 12-volt designs with single generators and crossed fingers. The V-2's electrical harness contained 8 miles of wiring, every inch of it carefully routed, bundled, and protected against vibration, temperature extremes, and electromagnetic interference. The system powered motor-driven valves, gyroscope platforms, ignition systems, and telemetry equipment that could transmit real-time flight data back to ground stations as the rocket climbed towards space. When Robert Goddard examined that V-2 in the Annapolis warehouse that afternoon in May, his trained eye immediately recognized features that paralleled his own pioneering work. Liquid oxygen and alcohol as propellants, turbine-driven centrifugal pumps, gyroscopic stabilization, blast vanes for directional control. In a letter to his longtime patron, Harry Guggenheim, Goddard wrote with barely concealed bitterness that still echoes across the decades. The Germans have used my patents. They've taken concepts I developed in isolation and built them at a scale I could never achieve alone. The V-2 is what my rockets could have become if anyone in America had bothered to listen to me for even 5 minutes. But Goddard, for all his brilliance and justified anger, missed the crucial distinction that other American engineers immediately grasped when they examined the evidence. The Germans hadn't stolen American technology and scaled it up. They had developed an entirely independent rocket program that, by 1945, exceeded American capabilities by nearly a full decade of concentrated development. Hermann Oberth's theoretical work in Germany had paralleled Goddard's American research without any knowledge of it. Wernher von Braun's team at Peenemünde had begun liquid fuel rocket experiments back in 1932, building on their own indigenous research tradition that stretched back to the 1920s. By 1934, their A-2 rocket had already exceeded Goddard's highest recorded altitude. The German program had state funding from the beginning, military priority status, access to Germany's finest technical universities and their graduates, and the labor of thousands of scientists and engineers pulled from every relevant discipline. Goddard's highest altitude achievement was 9,000 feet, reached in 1937 after years of struggle. The A-4 routinely punched through 50 miles of altitude, crossing into actual space before arcing down toward targets 200 miles away. Goddard's most powerful engine produced 985 pounds of thrust. The V-2 engine produced 60,000. Goddard worked with a handful of dedicated assistants in the New Mexico desert, funded by the Guggenheim Foundation, and met with complete indifference from the U.S. military establishment. The Germans worked at Peenemünde, a sprawling research facility that consumed resources equivalent to America's entire Manhattan Project. This wasn't a comparison between American technology and German technology. This was a comparison between one brilliant physicist working, essentially, alone in the wilderness, and an entire nation's industrial and scientific establishment, focused on rocket development as its top military priority. By June 1945, as American engineers continued their systematic examination of captured V-2 components, a consensus emerged in the classified reports circulating through the War Department's upper echelons. The United States faced a critical strategic vulnerability that threatened its post-war security. Rocket technology would define the future of warfare. That much was now crystal clear. The Germans had proven that ballistic missiles could strike targets hundreds of miles away, with absolutely no defense possible, no interception, no warning, just impact and destruction. The Soviet Union had captured Peenemünde itself, along with the V-2 production facilities and thousands of German rocket technicians who'd been unable to flee west. Unless America acted decisively and immediately, the post-war world would find the United States hopelessly behind in what was clearly the most important military technology of the emerging era. This brutal assessment led directly to Operation Paperclip, one of the most morally controversial decisions of the immediate post-war period that still sparks debate today. In September 1945, Wernher von Braun and 126 German rocket scientists arrived at Fort Bliss, Texas, under military custody, their backgrounds carefully scrubbed, their pasts quietly ignored. These men had built Hitler's vengeance weapons. Many carried SS ranks and had witnessed, even facilitated, the use of slave labor from concentration camps. Their rockets had terrorized London and Antwerp, raining down terror on civilians who never heard them coming. But they possessed knowledge that America desperately needed. And in the emerging Cold War, moral purity took a back seat to strategic necessity. The moral complexity of this decision troubled many Americans who knew the truth. These were Nazi scientists, some with blood on their hands, responsible for weapons that had killed thousands of innocent civilians. The prisoners who'd built the V-2s at Mittelbau-Dora had died in greater numbers than the rockets themselves ever caused, worked literally to death in those underground factories, while the Nazis built their revenge. Yet the Cold War was beginning, its chill already settling over Europe, and the Soviet Union had already begun rebuilding the German rocket program under Helmut Gruttrup, having captured their own contingent of German engineers who hadn't made it west. America couldn't afford the luxury of moral certainty when the Soviets were already moving. At White Sands Proving Ground, under the harsh New Mexico sun, work began on assembling captured V-2 components for test launches that would teach American engineers lessons they couldn't learn any other way. The first static test firing occurred on March 15, 1946, the engine roaring to life on American soil for the first time. The first actual launch followed on April 16th. At 2:47 in the afternoon, the reassembled German rocket lifted off from the desert floor. The guidance system failed almost immediately. A tail fin separated mid-flight. The rocket managed to reach only 3.4 miles altitude before tumbling back to Earth and crashing in a spectacular fireball. It was a humbling demonstration that even with German rockets and German scientists on hand to advise them, America still had an enormous amount to learn. Colonel Harold R. Turner, observing that first failed launch from the blockhouse, turned to his staff with words that captured the reality they all faced. "We have the hardware sitting right here. We have the men who designed it standing next to us. But we don't have the industrial infrastructure that originally built these things. We don't have the experience base that developed them through thousands of failures. And we don't have the institutional knowledge that comes from 6,000 launches." The Germans conducted that many test firings and combat launches combined. "We're literally starting from zero and learning as we go." Over the following years, 67 captured V-2s were launched from White Sands with varying degrees of success. 68% were considered successful by generous military standards, a failure rate that would have been absolutely catastrophic in actual combat conditions. But each launch, whether it succeeded or failed spectacularly, taught American engineers crucial lessons about rocket propulsion dynamics, guidance system reliability, high-altitude flight behavior, and the thousand engineering challenges of ballistic missiles that no textbook could convey. Scientists from universities across the country, from military laboratories, and from emerging aerospace companies sent experiments aloft on these V-2 flights. Instruments to measure cosmic radiation at the edge of space. Cameras to photograph Earth from altitudes no human had ever seen. Sensors to sample the upper atmosphere's composition. On October 24, 1946, a V-2 carried a 35mm camera to 65 miles altitude. And when the film was recovered and developed, it showed something humanity had never seen before. The first photographs of Earth from space. Grainy black and white images showing the curve of the planet, the thin line of atmosphere, and the darkness beyond. These images represented a historic first, but they also demonstrated exactly what German technology had achieved while America slept. The ability to send payloads beyond Earth's atmosphere and return useful data from the edge of space itself. But using captured German rockets was never meant to be the end goal. It was merely the bridge America needed to cross while developing its own indigenous rocket capability. In 1948, the Army Ordnance Department selected Redstone Arsenal in Huntsville, Alabama, as the permanent home for American rocket research. Wernher von Braun and his team of German scientists moved there from Texas, joined by growing numbers of American engineers, to begin developing missiles based on V-2 technology, but adapted to American military needs and manufacturing capabilities. The first major American rocket to emerge from this collaboration was appropriately named Redstone, a direct descendant of the V-2 bloodline. First tested in 1953, the Redstone incorporated fundamental V-2 principles: liquid oxygen and alcohol propellants, turbopump fuel delivery systems, gyroscopic guidance, but it also incorporated American improvements born from 8 years of painful learning. Better fuel efficiency, more reliable guidance systems. American manufacturing processes finally adapted to rocket production demands. By the mid-1950s, after a decade of desperate catching up, the technological gap was finally closing. American engineers had learned everything they could from German designs, absorbed the lessons written in V-2 hardware, and then begun moving beyond them with indigenous innovations. The Jupiter, Thor, and Atlas missiles represented truly American rocket technology, designed by American engineers, built by American companies using American materials and American manufacturing techniques that had finally evolved to meet the challenge. When the Soviet Union launched Sputnik in October 1957, the shocked American public saw it as a stunning defeat, but the engineers knew better. America responded with Explorer 1 in January 1958, launched atop a Jupiter C rocket derived directly from Redstone technology, which itself descended from the V-2. The lineage was unbroken. The Saturn V moon rocket that would carry Americans to the lunar surface in 1969 was designed by Wernher von Braun's team at NASA's Marshall Space Flight Center in Huntsville. Its F-1 engines produced 1.5 million pounds of thrust each, 25 times more powerful than the V-2 engine that had seemed so impossibly advanced back in 1945, but the technological lineage was absolutely clear to anyone who understood the engineering. Regenerative cooling for the combustion chamber, turbopump fuel delivery systems, gimbal-mounted engines for thrust vectoring and control, sophisticated guidance systems integrating gyroscopes and accelerometers, all concepts originally proven in the V-2, now scaled up and refined to impossible levels to achieve what Goddard had once dreamed about and what the Germans had made seem possible to accomplish. Looking back from our 21st century perspective, the V-2's legacy remains complex and deeply troubling. It was a weapon of terror that achieved minimal military value at an enormous cost in resources, slave labor, and human lives. The concentration camp prisoners who built these rockets under unspeakable conditions represent one of World War II's many atrocities that can never be justified or forgotten. Yet it was also undeniably the world's first practical ballistic missile, the first human-made object to reach the boundary of space, and the technological foundation for absolutely everything that followed in both rocketry and space exploration. For American scientists examining those first captured V-2s back in 1945, the experience was profoundly humbling in ways that shaped a generation. The United States, with all its vast industrial capacity, its scientific talent, its wartime mobilization capability, had been years behind a nation it had just finished defeating in total war. Robert Goddard's pioneering work, brilliant and visionary, had been systematically ignored by his own government while Germany invested the equivalent of billions in developing similar technology at industrial scale. The lesson burned itself into American consciousness and would shape military and scientific policy for decades to come. Technological superiority requires sustained investment over years or decades. It demands institutional support, not just individual genius, and it requires national recognition that individual brilliance, however remarkable, cannot substitute for organized, funded, supported national effort. When NASA dedicated the Goddard Space Flight Center in May 1959, Administrator T. Keith Glennon's words acknowledged both the American pioneer and the uncomfortable truth his career revealed to a nation that had failed him. Robert Goddard dreamed of rockets that could reach the moon and beyond. He built rockets that reached 9,000 feet on shoestring budgets and prayers. The Germans, working independently on the other side of the world, built rockets that reached space and terrorized cities. Today, America's space program builds on both legacies, learning from both successes and failures. But it also builds on the hard lesson that genius requires support, that vision requires resources, and that leadership in technology demands sustained national commitment, not just in wartime, but in peace. In the end, the V-2 taught America three critical lessons that echo through our technological development to this day. First, that rocket technology would define both military power and humanity's access to space for generations. Second, that technological leadership can be lost through neglect and complacency, and regained only through sustained, expensive, painful effort over years. Third, that in the emerging Cold War, the nation that controlled the high ground of space and commanded the long reach of ballistic missiles would hold decisive strategic advantage over its enemies. American scientists examining that first captured V-2 back in May 1945 saw all of this, even if they couldn't yet articulate it fully or understand all the implications. They saw the gap between where America stood and where it desperately needed to be. They saw the cost of ignoring visionaries like Goddard who'd been screaming warnings into deaf ears. They saw the future, captured in German hardware, waiting to be understood, absorbed, reverse-engineered, and ultimately exceeded through American determination and industrial might. The warehouse in Annapolis where Robert Goddard examined that V-2 with cancer stealing his voice is long gone now, demolished decades ago. But the rocket he saw that day, and the brutal technological revelation it represented, changed the entire course of American history. From that single moment of recognition, that painful understanding of just how far behind America had fallen while sleeping through a revolution, came the determination to catch up at any cost. The massive investment in rocket science that followed, the recruitment of former enemies to teach what they knew, and ultimately, the achievement that would place American bootprints on the moon just 24 years after Goddard stood in that warehouse, contemplating his own failure and his nation's wake-up call. The V-2 was Germany's vengeance weapon, designed to rain terror on cities that couldn't defend themselves. For America, it became something else entirely, something the Germans never intended, a wake-up call screaming through history, a teaching tool purchased in blood and moral compromise, and a challenge to do better, to go farther, to prove that technological gaps can be closed by nations willing to commit everything to closing them. The fact that Americans did eventually surpass what the Germans achieved, building rockets that carried humans beyond Earth orbit and planted flags on alien soil, proved beyond doubt that technological gaps can be closed. But the lesson came with conditions. It requires recognizing the gap exists in the first place, which demands humility that nations rarely possess. It demands committing the resources necessary to close it, which means sustained investment over decades, not just emergency spending in crisis. And it requires understanding that in technology, as in war, those who fail to invest in the future will inevitably be overtaken by those who do, by competitors who never stopped running while you convinced yourself the race was over. When Wernher von Braun stood at Cape Canaveral in July 1969, watching Apollo 11 launch toward the moon atop a Saturn V rocket so powerful it shook the Earth for miles, he reflected on the incredible journey from Peenemünde to the Sea of Tranquility, from Nazi vengeance weapons to humanity's greatest achievement. We always knew it was possible, he said, watching the rocket climb toward space on a pillar of fire that dwarfed anything the V-2 had ever produced. The physics were clear even back in the 1930s when we were just beginning. What changed between then and now was not the science itself, but the commitment. America in 1969 could accomplish what Germany in 1945 could not: focus the resources and will of an entire nation on reaching beyond Earth, not as a weapon of terror, but as an achievement of the human spirit, as proof that we could escape our cradle if we wanted it badly enough. That commitment, that national determination to catch up and surpass, began in dim warehouses and dusty desert proving grounds where American engineers examined captured German rockets with growing respect and confronted an uncomfortable truth that their nation needed to hear. They were years behind the curve. The only question that mattered was whether they had the determination, the resources, and the national will to catch up before the Soviets, who'd captured their own share of German knowledge, pulled so far ahead that the gap became permanent. The answer to that question would shape the world we live in today. The memories of World War II remind us not only of the price of freedom, but of the strength of the human spirit. Let us preserve their stories so they are never forgotten. Please subscribe to help keep these memories alive.